Welcome back. Let's move deeper into the chapter. We've already established the fundamental nature of the nucleus, its mass number, and the concept of binding energy. Now, we'll explore the forces that hold this incredibly dense core of an atom together. Nuclear forces are the fundamental interactions responsible for binding protons and neutrons within the atomic nucleus. They are incredibly strong, far surpassing the electromagnetic force at short distances, which is why the positively charged protons don't repel each other and break the nucleus apart. Two key properties define these forces. Firstly, they are short-range, meaning their influence is significant only within the nucleus itself, diminishing rapidly outside of it. Secondly, they are charge-independent. They act equally between proton-proton, neutron-neutron, and proton-neutron pairs. Understanding these forces leads us to the crucial concept of nuclear stability. The stability of a nucleus is determined by the delicate balance between the attractive nuclear forces and the repulsive electromagnetic forces between protons. Generally, nuclei with a specific ratio of neutrons to protons tend to be more stable. This ratio shifts as the nucleus gets larger, with heavier nuclei requiring a higher proportion of neutrons to counteract the increasing proton-proton repulsion. Deviations from this optimal neutron-to-proton ratio can lead to instability, prompting the nucleus to undergo radioactive decay to reach a more stable configuration. Thank you for joining us for this continuation. We hope this explanation clarifies these essential aspects of nuclear physics for your studies. Welcome back. From here, the chapter actually becomes interesting. The nuclear force is the incredibly strong attraction holding protons and neutrons together, overcoming their electrical repulsion. Nuclear stability hinges on the neutron-to-proton ratio. An imbalance leads to decay. Mass defect represents the missing mass converted into binding energy, the very force that binds the nucleus. We're diving deeper into the fascinating world of atomic nuclei, building on our last discussion. Today, we're going to unpack some core concepts that are absolutely essential for understanding nuclear physics and, crucially, for acing your exams. We'll be moving through these topics with precision, keeping things clear, sharp, and directly relevant to what you need to know. Let's start with the stability curve. Think of it as a map of nuclear stability. It plots the number of neutrons against the number of protons for all known stable isotopes. What does it show us? It reveals a distinct trend. Stable nuclei generally have a neutron-to-proton ratio that's close to 1.1 for lighter elements, and this ratio gradually increases to about 1.51 for heavier elements. This curve is incredibly important because it visually represents which combinations of protons and neutrons are most likely to remain intact over time. Deviations from this curve indicate instability leading to radioactive decay. Understanding this curve helps us predict why certain isotopes are stable and others are not, a fundamental aspect of nuclear behavior. It's the bedrock upon which our understanding of nuclear reactions is built. Now, for a crucial insight. Why heavy nuclei prefer fission? In one hard-hitting line, heavy nuclei, with their large number of protons and neutrons, experience significant electrostatic repulsion between protons, making them inherently unstable and prone to splitting, to achieve a more stable configuration. This repulsion is a powerful force that, when it outweighs the strong nuclear force holding the nucleus together, drives the nucleus to break apart. Fission allows these large, unwieldy nuclei to shed excess energy and become smaller, more stable entities. It's a natural drive towards a less strained state. Conversely, why light nuclei prefer fusion? Light nuclei, like hydrogen isotopes, have very few protons. This means the electrostatic repulsion between them is minimal. When these light nuclei are brought close enough together, the powerful short-range, strong nuclear force can overcome any remaining repulsion and bind them together. This process of merging, or fusion, results in a more tightly bound nucleus, which is a more stable state. The key here is that the combined nucleus is significantly more stable than the individual components, leading to the release of energy. It's like two small, energetic pieces fitting perfectly together to form a more solid, less energetic whole. This brings us to the binding energy curve, which is the real reason energy is released in nuclear reactions. The binding energy of a nucleus is the energy required to completely separate all of its nucleons, protons and neutrons, into individual free particles. Alternatively, it's the energy released when these nucleons come together to form a nucleus. The binding energy curve plots the average binding energy per nucleon against the mass number, the total number of protons and neutrons. What this curve beautifully illustrates is that nuclei with intermediate mass numbers around iron and nickel have the highest binding energy per nucleon. This means they are the most stable. When a nuclear reaction occurs, energy is released if the resulting nucleus is more tightly bound, meaning it has a higher binding energy per nucleon than the initial nuclei. For heavy nuclei undergoing fission, they split into lighter nuclei. These lighter nuclei have a higher binding energy per nucleon than the original heavy nucleus. The difference in binding energy is released as kinetic energy of the fission, fragments and neutrons, and also as gamma radiation. So, fission releases energy because the products are more stable, meaning they are more tightly bound. For light nuclei undergoing fusion, they combine to form a heavier nucleus. If this heavier nucleus has a higher binding energy per nucleon than the original light nuclei, energy is released. This is precisely what happens when light elements like hydrogen fuse to form helium. Helium has a significantly higher binding energy per nucleon than hydrogen isotopes. The excess binding energy is released, powering stars like our sun. The binding energy curve is the ultimate arbiter of energy release in nuclear processes. It tells us that moving towards the peak of the curve, towards the most stable nuclei, always involves an energy release. Let's connect these concepts to real-world examples linked to exam logic. Consider the uranium-235 fission reaction, a classic example often seen in exams. Uranium-235 is a heavy nucleus. When it absorbs a neutron, it becomes unstable and undergoes fission, splitting into two smaller nuclei, fission fragments, several neutrons, and a significant amount of energy. The exam logic here is to recognize that uranium-235 is on the heavy side of the stability curve. Its fission products are lighter nuclei, which are more tightly bound, higher binding energy per nucleon. The difference in binding energy between the initial uranium nucleus and the resulting fission products is released. This is why nuclear power plants use uranium as fuel. The fission process releases a controlled amount of energy. The exam question might ask about the energy released or the conservation of mass energy, and understanding the binding energy curve is key to explaining why energy is released. The heavy nucleus is inherently less stable due to proton-proton repulsion, making fission a favorable pathway to a more stable state. Another crucial example, though less directly harnessed for power on Earth currently, is gas solar fusion. Our sun is powered by the fusion of hydrogen nuclei into helium. Hydrogen isotopes are very light nuclei, far to the left of the binding energy curve's peak. When they fuse to form helium, the resulting helium nucleus is much more tightly bound, higher binding, energy per nucleon than the initial hydrogen nuclei. This increase in binding energy per nucleon translates directly into the immense energy output of the sun. Exam questions might relate to the energy source of stars or the conditions required for fusion. The logic is that light nuclei fuse to form heavier, more stable nuclei, moving up the binding energy curve and releasing energy. The immense gravitational pressure and temperature in the sun's core provide the necessary conditions to overcome the electrostatic repulsion between the positively charged hydrogen nuclei, allowing fusion to occur. These examples highlight a fundamental principle. Nuclear reactions tend to proceed in a direction that leads to a more stable nucleus, and this increased stability is directly reflected in a higher binding energy per nucleon. This is the core reason energy is released, whether through fission or fusion. We've covered the stability curve, the driving forces behind fission and fusion, and the pivotal role of binding energy. We've also seen how these abstract concepts manifest in tangible, real-world phenomena. This foundational knowledge is critical. Next, we move into the scoring numericals you cannot skip.
you.